Here we see TCal coding his, I don't even know. But like 90% of other developers, TCal uses Git. What'd you just call me? No, TCal, I'm not calling you a Git. I'm talking about Git, the software that you use to keep track of changes to your coding project. Oh, okay. With Git, you can share your project history with others and even revert back to a previous version if you were to make a catastrophic mistake. Anyway, TCal, like most developers, are lazy and don't even question the tools that they use every single day. They just go with the flow. Alright, bro, that's it. I'm gonna reinvent this tool from scratch just to prove these hater voices in my head wrong. Sup guys, it has been a minute. I would like to apologize to my 25 subscribers for being lazy and not uploading. School has been kicking me in the butt, but while I've been gone, I've recreated Git. Git is a version control tool that developers use to track every single change to their coding projects. It's used by high schoolers making their first to-do app, all the way up to machine learning engineers working at DeepSeek. Everybody is using Git to keep track of changes to their projects. Okay, quick demo. Let's say you're this very handsome young man and you want to make an audio visualizer. To start, you would go to your project directory and then run git init or initialize. Running this tells Git to start tracking this folder here as we work on it. So you go and you write your code, boom, boom, boom. And at the end of your session, you git add these files. You're telling Git to keep track of these changes. And once you're done adding all the files that you want, we git commit, which creates a commit of your project. You could think of a commit as a quick snapshot of the project with all its files and all the contents inside of the files. Over time, as you continue to work, add, commit, you accumulate a bunch of commits. So if we want to see all of those, we can git log, which gives us our entire project history starting from all the way at the beginning to all the way at the current time. What I just demonstrated right there is a typical solo developer workflow. Of course, Git has so many more features, considering it has 80,000 commits. And I'm one guy with about 3 weeks of time writing in C. So we're gonna keep it simple and just implement those 4 functions: init, add, commit, log. So of course, we're gonna initialize the video with init. Wait, TCal. You need to name your project. Okay, how about I name it Git Remake? Bro, that is boring as heck. Can't you think of something better? Ooh, I have an idea. What about... I don't know about that. No, it's pronounced T-it, standing for TCal's Git. Initting is arguably the most important function for T-it. Everything we do hinges on getting this right. We have to tap into the very operating system in order to... Yeah, I just wrote it. It was pretty simple. I can't lie. It took me like half an hour. Okay, so what's going on here? Let's just run it in C. T-it init and... TCal, nothing happened. That's because this function made a hidden folder. As a side note, adding a dot in front of any folder name makes it hidden in most operating systems. So with a little magic, let's see what's inside. Oh, there's just a few empty folders in this random file. But as you'll see when we implement the other functions, it'll become clear how this one folder and these few subdirectories allow millions of developers to version control. Alright, this entire project, of course, is tracked using Git. So all of the source code as well as the full version history is in the description at this GitHub. The init function I wrote is essentially just make directory, make directory, make directory. So yeah, now that we initted, we can go on to our next step, which is... Alright, adding is definitely a step up. It took me about 5 days to implement compared to half an hour for init. Anyway, as you'll recall, adding a file to Git is telling Git to track all the new changes you made to the file. You can think of adding as saving your changes into Git. So how the heck do we do that? 4 steps. We create a hash, we make a blob object file, we compress our file contents to put it into that blob file, and we put it into the index. Huh? What the heck does that mean? I think we should start with step 1. We hash the file we want to add. So we take all of its file contents and chuck it into a hash function. This hash function takes those file contents and spits out a 40-character hexadecimal string. This is our hash. It's created from the contents in our file. So any change, even a tiny period right here, will create a completely different hash. Now that we have our hash, we move on to step 2. Remember the folder we just made in init? Well, we go into it, our .tit folder, and then go into our objects folder that we made. And we create another folder inside of this using the first 2 characters of our hash. And then inside of that folder, we make a file with the file name with the remaining 38 characters as our file name. This is going to be our blob object, our binary long object file. Now that we have our blob, we go on to step 3. We go back to our original file that we're adding, and we compress all the data and put it into this object file. And once we're done all that, we move on to step 4. We put the original file name as well as the hash we just generated into our index. So this is our index, and no one can read that. The reason it's like unreadable is because it's binary data trying to be shown in a text format, which of course is difficult. So I rewrote it in this Google Doc. These 2 sections here are for metadata and data validation, so we're not going to worry about those. The real meat and potatoes are on the inside. So our index, in essence, is just a list of file names and hashes. These hashes, if you remember back to the previous minute of our video, are addresses of blob objects that we've made. So if we follow this hash into the objects folder, we'll find our compressed data inside of this file. So what we have is file names and file contents. Oh my, information overload. I know that was a lot, but adding in essence is just making an object file and then adding the file name and the hash into the index, which is all we need to do in preparation for our next function, commit. Boom. All right, beautiful. Now that we added all the changes we made and have a fully filled out index, we can commit. As you'll recall, committing is just making another version of our project. And I think the easiest way to explain this is just to look inside. When we run tit commit, this is what the object generated looks like. As you can see, our commit object has 4 sections: the header, the tree, the parents, and the metadata. I'll start with the easy sections. The header is telling us, yo, this file is a commit and it has size this many bytes. The other easy one is metadata. Whenever we commit, tit just looks at our computer and is like, yo, it was committed at this time by this person with the message here. The things that are a bit harder to explain are tree and parent. So let's get started with tree. This is a tree. Tika, that's not the tree we're talking about. This is a biological tree. Okay, fine. This is a tree. The astute among you will notice that it's freaking unreadable. That's because it has the same issue as the index, because it's binary data trying to be shown in a text format. So I'm gonna rewrite it right here. The astute among you will notice that it looks the same as the index. It's just file name, hash, and so on. The key difference is that trees are permanent while the index is continually changing. So what does that mean? I'll explain. So after we populate our tree by pretty much just copy pasting from the index, we hash it and create an object file, just like what we did for blobs. This creates a permanent copy of the tree inside of our .tit/objects folder. The index, however, is just one file, and it changes every single time we add a change. Therefore, the index is only useful for telling us what our current commit looks like. We need trees to tell us what our project looked like at certain commits in the past. So therefore, in each commit, we have a line dedicated to the tree, and then the hash our tree is stored in inside of our objects folder. Alrighty, let's tree explain. So what is parent? Git, and therefore tit, since we're copying, stores commits in a linked list format. When we create a commit, we add a line, parent, that points to the previous commit. Over time, we build a long line of commits with the current commit pointing to its parent, and then that one pointing to its parent, and that one pointing to its parent, and on and on and on until we get to our first commit, our initial commit. So with that, we filled out our entire commit with the header, the tree, the parent, and the metadata. So we do the same thing we do to blobs and trees. We hash and create an object file. So out of all of the commits that are in our objects folder, how do we know which one's the current commit or the head of the linked list? With a big all caps head file that we made in init. So if we look inside, we'll see that it contains a location in our references folder. And when we go into there, oh, look at that. We find a hash. And if we cat file this hash, we see the whole commit. And this is our head commit, the current version we're on. Okay, beautiful. With that, we have everything we need to make our commit. We have the tree we made, we have the parent commit, the metadata from the OS, and the header we generate. So now that we're committing versions and not arson, we can move on to our last function, which is the easiest way to show you how this works is just running it. /t at log, and out comes our log. So as we can see, we start from our current commit. It gives us the hash, who committed it, at what time, and then the message. And we move down the commit before, move down the commit before, all the way down to our initial commit. So how the heck do we do that? With the linked list structure, we go into our head file, which tells us where our head commit is. We read out all the stuff, the author, time, and message. Then we just go into a parent commits hash and repeat, and on and on and on until we get to the initial commit, which doesn't have a parent. That's simple. Okay, thank you guys so much for watching this video. For all you SWEs or programmers, I hope this helped you guys learn your tools a bit better. And for everyone else, I'm impressed that y'all stayed. Thank you so much for watching. I'm probably gonna lean toward more hardware embedded physical projects, but this pure soft one was pretty freaking fun. Yeah, subscribe, it's free. See y'all later.